Uh, Hello, Sheikh Jafar. Am I audible? Can you confirm if is my voice audible? Hello. Hello. Is my voice audible? Can you confirm once? So I don't know if my voice is audible or not because you are not responding anything. So uh, nonetheless, maybe I will just start, and as people join, we will see how it goes. Okay. So it's been 5 minutes since I started the recording. So nonetheless, I will start nonetheless. Okay. So just let allow me to connect my iPad to this phone. Okay. I think now it's fine. Okay. So I'll start sharing my screen. So my screen is visible to me. If it is not visible to you, let me know. Okay. I will reshare it. Okay, thanks. But I don't know, is there a lag between the audio because you are responding a bit late? Mm. So this is tutorial 4. All right. All right. So hello, namaste, and welcome everyone. Welcome to this tutorial. So this tutorial will revolve around week 4 and week 4 assignment. Uh, so let me just write this thing down. So this will be week 4. Okay. And till week 3 we were sort of revolving around feed forward networks and how do feed forward networks work. We saw how a feed forward network can theoretically approximate any function to the desired precision. Okay, so we saw all these things that how we can ensure that what should be the breadth of a layer so that we can ensure that a particular function is approximated and things like that. We saw many such questions last time, and most of these questions revolved around permutation and combinatorics and permutation. Okay, so you just need to you had to mostly solve some sort of counting problem to get the answers. However, week 4 delves into more theoretical stuff. We actually start getting feel of the technicalities involved in deep learning. Okay, So we saw, so in week four basically revolves around optimization. Yeah. And in particular, we saw different optimization schemes. So till week three, we saw gradient descent. Okay. We only saw that, okay, if we are sort of moving in the direction of the steepest descent, we are able to minimize the loss function. However, in week four, we see that, naive gradient descent might not be good. Okay, there are several problems associated with naive gradient descent, such as oscillation, convergence issue, and time taken for convergence in particular. And so in week four, we explored different different optimization schemes, so to say. So we saw momentum-based gradient updates, nested of accelerated gradients, and things like that. And we saw that, how each of these schemes sort of tries to tackle the problems of the previous schemes. So let me just write it down. Week four was mostly associated with optimization schemes. Okay. 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 So, so let us. So what I will do is, firstly, I will, maybe I will recap all the updates, optimization schemes that we saw, and then we will jump to questions of assignment for week four. And if you have any questions, you can just unmute yourself and ask questions, or maybe you can even comment in the chat. That is also fine with me. In case you have any issues with audio, or screen is not visible or things like that, you should just unmute yourself and let me know. Okay. So let's get started. So the first scheme, I think, that we saw, that we already knew sort of from week four, was vanilla gradient descent. This is vanilla gradient. Someone is saying that screen is not visible. Mm, I don't know why this issue is happening, because whenever someone joins after uh, the meeting has started, he is not able to see the screen. So I had to, I think, stop sharing and then restart and do things like that. So let me just do it. Okay, I will do it. If possible, maybe speak up. Okay. Okay. So is the screen visible now?
Yeah, it's visible now.
Okay. So okay. So the first thing that we saw was vanilla gradient descent. We sort of already knew this from our uh, previous week's assignment. So what is the scheme here? The scheme here is that, what we will do is, at time instant t, we will take the previous updated weight vector wt minus 1, and sort of use a step size, something called learning rate eta, which we denote by eta, and take the gradient of the loss function with respect to wt minus 1, and kind of update, use an update tool like this. Okay. So this was the vanilla gradient descent, or equal, if I increase the time index, we can also write this as wt plus 1 is equal to wt minus eta times gradient with respect to wt loss function at that instant. Okay. And and so we, in the lectures, the notation is like, so the notation that we chose was, we use something like this: gradient with respect to this wt. We wrote something like this. This is to, just make sure that we are not lost in uh, notations. This notation is very simple, so we will use this one and throughout the lecture. Okay. So this was the vanilla gradient descent. Okay. But we saw, that there are problems with vanilla gradient descent, in particular when the slope, when the curvature of your loss landscape is very flat. in the sense that so you, let's say you have some loss function which looks something like this. So something like this, something like this. So perhaps here is your minima. However, you are starting from here. Okay, you are starting from here. The issue with these methods, vanilla gradient descent in particular, is that it takes very the grade. So I hope you can see that the gradient here is very small. Okay, the gradients here are very small. So it will take a lot of time and steps to actually go towards the minima which is present here. So what is this called? Flat curvature. So this is the problem with vanilla gradient descent. To overcome this issue, what we said that okay, well, we know that sort of that I have to go in this direction, and I am repeatedly updating my weights to go in this direction, right? Again here and again here, and so maybe I can use the past history, the history that I have, the history of my update steps time till this till this time instant, to sort of make a guess that okay, should I go here in a so should I take a larger step here, or maybe I should take a smaller step here, things like that. And we termed this as what call we call this as momentum based gradient update. Okay, so the momentum based gradient update was a smart trick. Okay, so this is also known as the heavy ball algorithm. So the idea is, if you see a ball, when it actually descends on a curved surface, its velocity keeps increasing, in this, because it has some acceleration from due to gravity or any force. So the motivation is taken from there. So the idea is that if you are moving in a particular direction for a long time, for a lot of time. Okay, so the idea is that if you are moving in a particular direction for a lot of time, you should gain some momentum in that direction. Okay, so in this particular example, if you are moving here again and again, so maybe you should gain some momentum and cover bigger steps now, things like that. So I hope the intuition is clear. Okay, so mathematically speaking, what we did was we defined something as updates. Okay, update t minus one. We said that okay, sorry, update at time t should be equal to gamma times. Okay, okay. I think I am admitting all of these people. Okay, yeah. So the idea is that at time instant t, you estimate your update step. So, let me mute you. Yeah, so at time instant t, you calculate what your update is going to be, and the update is something like this, right? So update t minus one plus eta times gradient with respect to wt. Okay, so this is the update that you do at time instant t, and your weights are updated in the following way: wt plus one is equal to wt minus update t. So I hope you can see that the current update is not only dependent on the current weight, right? As was the case here, right? At time instant t, the only gradient that we were using was with respect to the time instant t, wt, right? Here we are also taking the previous time of updates that we have done till time t into consideration. Okay, this term in particular. And I mean, one way to see it is that you just write down your update. So let's say update at time zero is zero because you have not done anything. Update at time instant one will be gamma times update at time instant 0 plus eta times gradient with respect to w1, which will be equal to eta times gradient with respect to w1. Similarly, you can keep writing the update steps. Update at time instant 2 now will be gamma times update update at time instant 1 plus eta times gradient at time instant 2, which is equal to gamma times. So what we will do is we will just substitute this term here. What we will get is gamma eta times gradient with respect to w1 plus eta times gradient with respect to w2. So I hope you can see that the at time instant t, we are not only considering the so at time instant 2 in particular, we are not only considering the gradient at time instant 2, but we are also considering the previous past updates, which is gradient at time instant 1, right? And if you keep writing, you will see that the general update step at time instant t is something like gamma raised to t minus 1 eta times gradient with respect to w1 plus gamma raised to t minus 2 eta times gradient with respect to w2 plus dot eta times gradient with respect to wt. So now the picture is bit clear, right? We are not only at time instant t, the update does not only depend on time, the current gradient, but it also depends on the past gradients. How does it depend on past gradient? This is the formula that should give you the overall picture. Okay. So this was momentum based gradient update. Okay. But we saw that we observed that the problem with such update rule is that there are a lot of oscillations. If you watch the lectures, someone is saying that my screen is not shared. Actually, my screen is shared. I can see my screen. However, let me stop presenting and then I will reshare it. So let me know if the screen is visible now. Uh, is the screen visible, Ravi Chandra? Okay, yeah. So I don't know what the issue is, but generally, if you join after the meeting has started, you are not able to see the screen. That is my general observation. I am not sure why it happens, but yeah, there is some issue with this Teams. I am not sure how to resolve it. If anyone of you knows these things, so maybe you can help me out. Okay, so moving on. So the problem, as we were discussing, the problem with momentum-based gradient updates is that you are not able to. You observe a lot of oscillations, because of which you are not able to exactly converge to the minima. You are around the minima. Okay, you are around the minima, but you are not exactly at the minima. You are sort of oscillating at the minima. That is the issue. To resolve that issue, uh, what we saw was nested of accelerated gradient. So you can see my handwriting, right? Can you just confirm that once? What I am writing and things like that. I can see you, but you are not. But you are not seeing what you are writing. Uh, okay. Again, some issue. Frozen page is visible. Okay. Let me again stop the sharing. Okay. I stopped the sharing. I hope it is okay. Right. Now I will share my screen. Start the broadcast. Okay. Is it okay now? Okay, thank you. So sorry for these hiccups. I am not really sure why Teams has this issue, but I cannot do anything about it. So okay. Okay, so we're talking about nested of accelerated gradient. So the idea with nested of accelerated gradient is that, so the idea is of look ahead. What is look ahead exactly? So so think of it like this. You know that you are so let's say you are around some minima. Okay. So let me draw something. Maybe I don't know how to draw it, but let me try. Okay. So let's say this is the minima, and you are at this point here. Well, you know that at this point you are. If you take a step, maybe you will go somewhere here. Okay. However, if you know this thing, maybe, and you know that you are kind of moving away from the minima, which is here. So the a clever strategy would be to sort of not go there, and maybe correct your step and move here, something like this. I hope the idea is clear. The idea basically says that if you know where you are going to go, which is this point, adjust your step such that you don't go this far. You go, I mean, make sure that you are close to your minimum, which is this. So this is the general idea. Okay. And how we manifest this idea is the following. Okay. So what we do is we calculated w look ahead, which is wt minus gamma times update t minus 1. Okay. So I hope you can see that this is similar to yeah, so I hope you can see this is similar to this part, so the momentum based gradient descent part. You are doing a simple momentum based update for the first time, but this, you are not actually updating your w. So notice that this is w look ahead and not wt plus 1. This is not wt plus 1, it is w look ahead. What it means is that you are kind of storing something. This is just for our reference. We are just calculating it for our reference. And what do we do with this w look ahead? We calculate our new update. Sorry. So our new update at time instant t is gamma times update t minus 1 plus eta times gradient with respect to w look ahead. So the idea is that so if you so you so w look ahead is this point. Okay, so this is so let me maybe write few things. So this is sort of wt. Okay, the current point. This is your w look ahead. Look ahead. Okay. So you have calculated W look ahead before time. That is why you are calling it look ahead. You are looking ahead in time. And at W look ahead, you know the gradient, what the gradient is. So, so this part is the gradient at this point. So I hope you can see that this point is the gradient will be in something like this direction. Okay. And since you have seen this direction, the direction of this gradient, you are adjusting your step. You are saying that okay, my overall gradient will be something of, will combine this step, okay, this step plus this step, which takes you here. Okay, so let me write this down. So this is uh, so what is the final update? Wt plus 1 is equal to wt minus update at time t. This is the final grade update step, and this is your WT. Okay, let me use blue color. This is your WT. So I hope the idea is clear that at any time instant, you look what your gradient, where you would have landed if you didn't use nested or anything. You did a naive momentum based update where you would have ended up. This is that point. At this point, you see what is the gradient. Okay, and after seeing this gradient, you adjust your time step, adjust your update, and reach a point which is closer to the minima, which is this point. Okay. So I hope the idea is clear. If not, please unmute yourself and let me know what if I was not clear. Okay. So this was Nesterov accelerated gradient. And after Nesterov accelerated gradient, we saw that we can also make the learning rate that is involved in most of the parts are fixed. However, learning rates play a very crucial role in deep learning. In particular, the step sizes are very crucial to achieve exact convergence. And so there are algorithms. So then we saw some algorithms which are which are fine tuned to adjust their learning rates. Among those, we saw what is called as AdaGrad. Yeah. So what was AdaGrad? AdaGrad said that okay, as we so if in a if there is some direction in which you are going for a long time, okay, maybe you have converged there and there is a very little scope to move in that particular direction. So what is the idea? The idea is as follows. So suppose there is something like this, and you are moving here for a long time. You are moving here for a long time. So after since you have moved here for a long time, perhaps there is not a lot of scope left to take big steps, perhaps. Okay. So in that case, what you do is that using this information, what you do is you kind of say that okay, maybe I should restrict myself to a lower step size. And how is that manifested? So it is manifested in the following way. So you construct something like vt is equal to vt minus 1 plus int of respect to wt whole square. This is some quantity that you define, and you update your wt as follows. So wt plus 1 is equal to wt minus eta upon square root of pt plus epsilon gradient of wt. So maybe what you can do is think of this as some eta dash, okay? And your if you consider this as eta dash, this is nothing but your normal gradient descent. I hope you can see that. However, this eta dash is not constant anymore. It depends. It has a time dependency here, and this time dependency is seen here. Okay, I hope the idea is clear. The idea is that if you are moving in a certain direction for a long time, suppose this, right? You are moving here, and then again moving here. So you have missed your minimum. So maybe you can use this information to reduce your step size and just move here. So that is the idea of AdaGrad. So adaptive gradient is what AdaGrad stands for. Similar to this, we saw something called RMS prop. The RMS prop algorithm was he said that okay, you are giving in this update step you are giving equal weightage to the past and as well as the present. So VT minus one is the past information, and gradient of WT whole square is the present information. And RMS prop said that okay, this is not desired because maybe you want to give some weightage to this, some weightage to this. Why should they be equal? So to avoid this, you updated your VT and said that okay, my VT will be a linear combination of these two terms, 1 minus beta gradient with respect to WT whole square. And using this new VT, you updated your WT, VT plus epsilon gradient with respect to WT. Right? So this is the idea of RMS prop. Okay. So a very minor change, as you can see. So I hope if you observe these two equations, only difference is that you are multiplying with something beta and 1 minus beta. This thing comes because you don't want to give equal information to these two terms, as is the case with AdaGrad. Okay. And after doing all these things, you said that okay, we have two regimes now. One set of algorithms, which is the which sorry, one set of algorithm, which is this one, actually relies on adaptive learning rate, adaptive step size. Whereas this there are another set of algorithm is this one which actually relies on adaptive uh, directions, so to say, right? You are using something, your updates are changing. So well, then someone said that okay, why not combine these two ideas? Why not use adaptive learning rate as well as adaptive gradients? Okay. And so that led to the rise of what we call as Adam optimizer. And nowadays in deep learning, this is the most we use this a lot. This optimizer is something that we use a lot, right? So what is the Adam algorithm? Adam algorithm is sort of combination of the two paradigms. Okay, so you say that okay, your momentum is beta mt minus 1 plus 1. So this is beta 1, this is 1 minus beta 1 gradient with respect to wt. This is similar to the heavy ball algorithm. I hope you can see that. A heavy ball or adaptive gradient, momentum based gradient. Okay. And you said that okay, now I don't only want to update my gradients, I also want to update my learning rate. So your learning rate, you updated the learning rate as follows, which is you basically copied the learning rate from RMS prop, which is 1 minus beta 2 gradient with respect to wt whole square. So okay, I mean, let me just point out that this is coming from momentum. Okay, and this is coming from RMS prop. So it's like you are clubbing the algorithms, nothing more. And you are saying that okay, you are doing some sort of free scaling. Mt hat is equal to 1 over 1 minus beta 1 raised to t. Bt hat is equal to Vt over 1 minus beta 2 raised to t. This scaling is required to make sure that your estimate is unbiased. And then you said that okay, now my wt plus 1 is equal to wt minus eta upon square root of vt hat plus epsilon mt. So I hope you can see that this is your adaptive gradient or momentum based gradient part, and this is your adaptive learning rate or RMS prop part. Okay. So if you have any questions till here, these are the basic ideas of the optimization schemes that we generally use. And I thought that it would be a good idea to recap these algorithms, because we will be mostly relying on these algorithms to solve assignment for questions. So if you have any questions related to this part, maybe you can unmute yourself and ask questions. Okay. I will allow you to ponder over it. If you have any doubt, maybe you can ask. Till that, maybe I will take some sip of water. Okay. All right. So so if you don't have any questions, maybe I will continue. So so let's start with the assignment problems that were there. Okay. So I will start with assignment problems. So there are 10 questions. Let's start with the first questions. Okay. So, okay. So what is the first question? The first question says that okay, we are training a neural network using a normal gradient descent algorithm. Okay. So it is a vanilla gradient descent. Okay. We observe that the change in weights is small in successive iterations. Small change in weights. Okay. What are the possible causes for the following phenomenon? So since we are using vanilla gradient descent, the first thing maybe that you should write down is the update step for vanilla gradients. What is the update step? Update step is the following: wt plus 1 is equal to wt minus eta times gradient with respect to wt. This is your update step. Okay. Then you are saying that there is a small change in weights. Okay. So what is the change in weights? You can calculate the change in weights by taking this term on the left hand side. This will become Wt plus 1 minus Wt equal to minus eta times gradient of Wt. Since we are only talking about the change and not the sign, we can take the mod on both sides. Okay, Wt plus 1 minus Wt mod is will be mod of eta times gradient with respect to Wt. Okay. Now someone is saying that okay, this term that I have here, this is the uh, change in weight, right? This is the change in weight, and someone is saying that this is small, right? So what does that mean? That means that okay, this term on RHS should be small. Okay, I hope that is clear. No big nothing mathematical here. If the left hand is left hand si- if LHS or left hand side is small, your RHS or right hand side should also be small. Okay. So now we know that okay, eta times gradient with respect to WT is small. This is what we can conclude, right? So what are the possible reasons because of which this term can be small? So we can see that it is multiplication of two terms. I hope you can see that eta and gradient with respect to WT. If the product of two numbers is small, what does that mean? Either one of them is small or both of them are small, right? These are the only possible cases. So, for example, let me give you some examples. So imagine 10 into 0.1 or maybe 0.01. This gives you 0.1, right? So now the output is small. This is a small number. So here, why is it small? 10 was not small. However, the second term here was small, right? So I hope you see my point that one of them was small. Or maybe what can happen is that, maybe 1 into 0.1, something like something like this can also pop up. This will also give you 0.1. Now the output is small. However, this time both the inputs were, I mean, 1 as well as 0.1 were small, right? So this is the like the common logic that I am trying to use here. Okay. If this is not clear, maybe you can unmute yourself and ask. Nothing fancy here. Okay. So what are the possible cases? This implies that either eta is small, right? First term is small. Either gradient with respect to Wt is small, or both eta and gradient with respect to Wt are small. These are the only possible cases. And in the options, you have options. Uh, the options that you have been given are eta is large. Eta cannot. So we cannot say if eta is large or not because we know the product is small. We don't know what the individual terms are, right? What we can say is that at least one of them is small. We cannot say one of them is large or not. So eta is large is not a possible answer. There is an option which says gradient with respect to w is large. That is not also that is also not a correct answer. However, the other two options which correspond to which correspond to this and this, which says I gradient with respect to w is small and eta is small, only these two options are feasible or possible. So our answers will be what B and D. Okay. If you had any, if this was not clear, maybe unmute yourself and ask questions. Okay. So if not, I will move on. So let us see the second question. So maybe can you just for a check, can you just comment if I am audible or not? Because it feels very weird to not hear anything and just keep talking. Can Okay, audible. Thanks. This is just for my sanity check that maybe I am speaking something and it is not audible to you, then there is no point of for this. Okay. So the second question says that if we start the gradient descent from point C, which of the following is most likely to be true? Okay, so let me draw that diagram that is given here. So you have a big mountain like this. You have a valley, then again a small mountain, a small valley, a relatively bigger mountain, and then it goes down. Something like this is given to you. Now you have been given some points on this graph. This is A, something like this is A dash. You have been given C, which is somewhere here. Something like this is B dash, and this is B. Okay, this is given to you. Okay, so let me draw the axis. Now you are asked that if you start from this point C, where will you land? Where will you converge? So I hope that the idea of gradients is clear to you by now. The gradient at any point. So okay, lot of things happen. So what the hell? Let me see if this was okay. This somehow. So is my screen unshared now? Uh, I don't know. Seems that my screen is unshared because I cannot see it on my. Yeah. Okay. Uh, internet issue. Just give me a second. It seems that there is a internet issue because I'm really sorry for this. I don't know why this is happening today. Mm, okay, thanks. So my tab somehow got disconnected. I'm sorry, guys. I don't know why. There is some issue with institute. Uh, with institute. Uh, yeah. So now it should be visible. Okay. Yeah, so what I was saying was that you have been given this graph and you have been given some points and you are asked that if you start from this point C, where will the gradient descent converge? So I hope that you are sort of remember what the idea of gradients is. The idea of gradients is that at any point, let's say this point, you will uh, via gradient descent, you will move in a direction which minimizes your value. So if this is the point at which you are, you will move in this direction. So just look. So a simple thing to do if you want to see where you would go, just keep that point and draw a tangent at that line and see the value and see the direction of tangent which decreases your value, which will be this point, which will be this direction. Okay, so so since you are at point C here, you will go in this direction, right? I hope that is clear. So let me just draw it with pen as well. So this is the direction that you will go, right? This direction, and you will eventually reach at B dash. However, at B dash, since B dash is a local minima, there here if you draw a tangent here, okay, there is no direction in which if you move your value will decrease. Okay, so this is a local minima and you will get stuck here. Okay, so this is the point at which you will converge. Okay, so so let me write that down. If started at C, you will converge at B dash. I hope this is clear. One could have also asked that, what if you start at A? So the idea is again the same. At A, you draw this tangent. You see which direction decreases the value. I hope you can see that again A has no direction in which you can further decrease your value because the values in plus minus delta direction will be the same. In general, if you are at some sort of optimum, if you are at either at maxima or at some minima like this, you won't be able to, your gradients will be zero because your tangent will be a straight line parallel to the axis. Okay, and hence you won't be able to decrease your value. That is the whole idea of gradients. Okay, so if you have any question, again, just unmute yourself and speak up. Okay, otherwise I will move to the third question. so so what is the third question? The third question says that you are given a data where one column has most of its value as zero. Okay, what algorithm should we use here for faster convergence and achieve the optimal value of the loss function? All right. So what are the options? So whenever you see something like most of the values are zero, the concept that should come to your mind is something called sparsity. Okay, let me write that down. Sparsity. So what does sparsity means? The English meaning of sparsity is that there are very low density assumptions. For example, a fact that I remember is that Arunachal Pradesh has a sparse population. What does that mean? If you look at a certain area, there are very less people in that area. Sparsity means that the values are not dense or they are scattered things. Sparsity in English means that. In mathematics, what do we mean by sparse? By sparse we mean that most of the values are zero. Okay, most of the values are zero. This is what we mean by sparsity, and that is what is given in the question as well. Okay, uh, so what are the options? A, nag, which is nested of accelerated gradient. B is Adam. C is stochastic gradient descent (SGD), and D is momentum momentum based gradient descent. Okay. So among these options, let us try to recall. If if your data is sparse, okay, think of it that your data is given to be sparse. So what does that mean? That I mean, if you remember from the lectures, we know that when the data is sparse, you have something called sharp valleys, and in sharp valleys, an algorithm like Adam works the best. If you don't remember it, maybe you can go and rewatch the lectures. But it is a fact. It is kind of a fact that uh, if you have a sparse, so to say. uh, if you have a sparse vector and you want to update that vector to get to the lowest value, an algorithm like Adam works the best. Why will it be the best? The reason is that it takes into account the momentum based updates as well as the momentum based learning rate, as we saw here. Okay, this thing that we saw here, this is the essence of it. uh, so I cannot draw that diagram, but if you remember, there was something like this, right? if if your valley is very sparse, your valley goes something like this, something like that, where The ideal direction should be like this, this is how you should have descended. However, if you use other algorithms, they will keep bouncing on these walls. Something like this will happen, and your convergence will be very slow. Adam makes sure that you kind of move on this valley. Let me draw that. This will be the Adam's path. Okay, whereas the other algorithms, they will sort of oscillate here. Something like this will happen. So this is called pathological valley. Okay, this is the problem that is faced by other algorithms. Why does it happen? Maybe you can go and rewatch the lecture if you don't remember. If you have any doubt, you can ask me. Okay, however, I will assume that you know this, and I will move on. Okay, because the explanation is a bit mathematical. If you don't remember, rewatch the lecture. If you have some doubt there, maybe you can ask. Okay, so this Adam will be the correct answer. So whenever you have a sparse data, the go-to algorithm is Adam optimizer. Okay, so just you remember this as a fact, perhaps. If not, you can also remember the mathematical explanation for it. Okay, so the fourth question is, in the given contour, which among the given regions is the steepest region? Okay, so you have been given a contour plot. So let me just try. I will try to draw this. Okay, I don't have a good handwriting or something like that. Or I will try. So these are the two things. So you have been given something like this. You have something like this, and then the color changes to red. Okay, okay. So you have been given a contour plot like this. So this is not exactly how the curve looks like in the question, but pardon my drawing, and maybe this will be good enough to. I hope that it will be good enough for explaining stuff. Okay. So this is the region one. This is the region two. This is the third region, and this is the fourth region. Okay. And we are asked that which among the following given regions is the steepest region. What do we mean by steepest region? Okay, whenever we are given something, whenever we hear something like steepest region, okay, what does it mean? This the So the question is trying to ask you us about highest gradients. Okay, so if the gradient is high, that means the it is more steep. For example, if I tell you about these two things, okay, this is one graph and this is another graph. Okay, I ask you which of the graph has more steepness in it. I hope you will say that this graph has more steepness because it is more inclined. Okay, however, this doesn't have a high steepness because it is more flat. Okay, uh, so this is what we mean by steepness, high grade.
दूसरी बात आपने ये भी देखी होगी प्रधानमंत्री मोदी
Okay, now uh, apart so for this given contour plot. So okay, let us remember what the contour plot meant. Okay, what does this even depict? So what this depicts is that, okay, each of these curve, right, this thing, what it shows is that this is a so there is a function. Imagine a three-dimensional function that is coming out of it. Okay, so perhaps you can imagine something like this. Okay, something, a bowl like this, a bowl like this perhaps, and a bowl like this here. So maybe more appropriate diagram would be something like this. So you can think of something like this. This is a two-dimensional thing, but imagine it in 3D. Okay, there are so this is not just a parabola, but it is a paraboloid. So it has a three-dimensional structure to it, and it is growing here. It is then going and coming here. Okay, each of this curve denotes that, okay, in this three-dimensional bowl, this is a path which has the same value. Okay, so whatever value it is, let's say some 1.5. So if I see this curve, okay, and I cut the curve at let's say 1.5, I will get this circle as a path. Okay, this is what contour plot mean. Imagine the 3D curve, and I hope the my message is clear. I cannot actually draw it. It will be difficult for me to make that drawing, but I hope the idea is clear. So since this shows that it is getting some, so this path has same value, this path has same value, this path has same value, things like that. Okay, so what can I conclude from it? It should be something like a paraboloid, right? Something like this, but in 3D, right? I cannot draw it exactly, but it will be difficult for me. But nonetheless, I hope the idea is clear. It will be a bowl here. Similarly, this two, the second region will also be a bowl again, because it is similar to this blue region, but just on the right side of it. And these two paraboloids are connected via a bridge. So this is the first parabola, and this is the second parabola. These two are connected via a bridge. This is the bridge, okay, which is the third region that we are seeing here. And fourth region is something which is again somewhere far here. So how would you judge, where is the steepest gradient? So the way to judge this is that if the gradient, if a region is steep, okay, what does it mean to have a steep curvature? It means that if I'm at this point, even if I move a little bit here, okay, I will change my value. If I move a little bit from here, I will change my value. My So in some sense, my change in values will be very rapid. However, when the region is flat, for example, let me take even something like this. Okay, this is a flat curve. Okay, if I am here, if I move a little bit here, my change in value is not that high. Okay, my change in value is very little. Okay, however, here if I move a little, my change in value is very high. So this is how I can use this curve to judge which is the steepest region. So at point one, I can see that let's say I'm at this point. If I move here, this is the path which has same value. Okay, it doesn't have a lot of differences. If I move in this direction, sorry, if I move in this direction, I will land on the same value because this is a level curve. All these all the points on this curve have the same value. Similarly, here also, the curve has same value. So this is not a steep steep curve, so to say. Same thing goes for the second region as well. And in the fourth region, so in the given diagram, it is there are not a lot of change in values because the level curves are not present here at all. So most probably, this is a flat land, which where there is no change in values. Okay. However, if we see the third region, which is this one, if I move a little bit here, I land on a second, another level curve. If I go here, I land on another level curve and things like that. So this is a more steep region. If you didn't understand what I just said, just maybe draw the diagram and we will see what it is. So this is the region which we are saying that is steep as compared to this region or this region. This is the idea. So think of two paraboloids. These paraboloids are connected by this third region, and that is why the third region has more steep. So there is a lot of imagination involved in such questions. There is no systematic way. You need to imagine it in 3D. What is going on? Things like that. So maybe I will just write down that region 3 has steepest curve. Okay. So that will be the right answer. If there was some doubt, maybe if you ask me some specific doubt, what was not clear, I will be able to explain it. However, this is the best that I think I can explain without, having any point in mind. So let us see the fifth question. The fifth question says that if gamma is greater than or equal to 1, gradient with respect to W is greater than or equal to 1, and this is the first gradient. First gradient. What is the first gradient means? This is gradient W1, okay? In a momentum based, so this is a momentum based uh, gradient. Okay, this is given to us. Then which of the following statements are true? Okay, so so now, okay, so what I will do is I will copy something that I already said. This thing. Okay, let me just copy this. Copy, and I will just paste it here so that I don't have to write this again. Okay, so we are given that the value of gamma is greater than 1. So what does that mean? So I hope you remember that so let's say I am at some time instant t. If the value of gamma is greater than 1, gamma raised to t minus 1 will be very large number. Will you agree with that? Because if so, let's say you have something like 1 point, so let's say something you have gamma equal to 2. If gamma is greater than equal to 1, I can take any value. So let's say I take the gamma to be 2. Now let's say I'm at time instant 100. So gamma raised to 100 will be equal to 2 raised to 100, which is a large number. So this will be very large. Why gamma greater than 1 is a sort of important condition. Let's say if gamma were less than 1, something like gamma is equal to 0.5. Now gamma raised to 100 will be what? 1 by 2 raised to 100, which will be 1 by 2 raised to 100, which will be almost equal to 0. So this thing which I am writing as large would have been very small. So that is why this condition that gamma is greater than 1 is important for us. Okay, since gamma is greater than 1, this term is a large quantity. Okay, now we are also given that this thing, the gradient of W1, this quantity is also greater than or equal to 1. Okay. Now we are asked some of the following. We are given some options. So what are the options that we are given? So what we can conclude? Okay, what we can conclude is the following: that this term will have large domination, domination. So this will be a dominant term. That is what I mean. Okay. Okay. So what are the options? The first option is W will converge to local minimum. Well, I mean, there is no evidence for this thing, right? I mean, we don't know why should it converge to local minimum? We don't know anything, right? I mean, all we know is that this term will have a lot domination. I mean, this will be the dominant term. We can maybe ignore all this term and maybe just use this term. However, this does not ensure that I will go to a local minima, right? So, I mean, this is clearly a wrong statement to say. I mean, we don't have enough evidence for this. Second option is W converges, W converges to global minima is what it is saying. I mean, we are not able to, sufficiently say will it go to local minima or not, and this option is claiming that we will go to a global minima. That is again, not correct. I mean, we don't have substantive proof for this statement as well. So this is also not a correct choice. Third option C is, W oscillates oscillates around local minimum. I mean, again, for this also we don't have any substantial evidence. I mean, first of all, we don't know that we are close to local minima or not. Okay, that is the first thing. So I don't know if I'm closer to local minima or not. And on top of that, this option is saying that okay, I will oscillate around it. I mean, again, I hope my idea is clear, right? I cannot say if I am near to local minima or not. This option is saying that I will not only be around the local minima, but I will oscillate around. I mean, I don't have evidence for that as well. All we know is that this will be a dominant term, and this won't contribute as much as this term. Okay, So I mean this is also not a correct. So all of these are incorrect. So there is a D option which says none of the above. So this is the correct option, evidently. I mean, so I hope you can see that I have no information about this thing. So like unless and until I know that I'm closer to minima or something like that, I cannot comment on any of these three options. That is all this question wanted to sort of tell you. Let me know if there was some doubt. If I was not clear, I will maybe answer your question. If not, I will move forward. Okay. There is a sixth option which says which of the following algorithm will result in more oscillations on parameter during the training process of the neural network. Okay, uh, so we are asked about more oscillation. Okay, more oscillation. What are the options? The first is SGD, stochastic gradient descent. The second option is mini batch SGD. Okay. The third option is batch gradient descent. Batch gradient descent, and D is batch nag. Nag is Nesterov accelerated gradient. So I hope the idea of I hope that from the lectures you know what is the idea of stochastic, making anything stochastic. Okay, so uh, so the idea, right? Okay, so here was the thing, right? So let me just draw this line here. So ideally, what we want is that Wt plus 1 is equal to Wt minus some eta times. What we practically want is that we want to take sum the gradients of the loss function with respect to Wt, and the sum is over I equal to 1 to n, and we divided this by 1 by n. Okay. So this is the full. So what does this mean? Okay. Uh, okay, maybe what I will do is I will erase this because this I think has not been taught yet. Okay. The idea is to take the gradient with respect to Wt and loss of all the capital X and Y, and this means the whole data. So this is the ideal gradient descent. Vanilla gradient descent, or the ideal gradient descent wants you to calculate the loss function for the entire data set. Okay. So if I have a big data set, let's say with thousands of data points, this gradient descent actually asks me, calculate the loss for all the points in this data set. Okay. And try to minimize the cumulative loss, which is the entire loss that we have. Okay. However, the issue with this is that calculating the entire loss for all these data points will be very computationally inefficient, because you will have to pass through let's say a millions of data set or thousands of data points, which will be very inefficient. So to efficiently calculate this, what we do is that, okay, instead of taking the entire data set into consideration, we take, let's say, only a few samples of it into consideration. So we will take just two samples, or one sample, three sample, 10 sample. It is up to me. So there, this introduces some sort of stochasticity. Okay. And because of this stochasticity, it is named as stochastic gradient descent. So SGD uses only one sample. Okay. Mini batch SGD uses some mini batches. So let's say if the batch size is something like B samples, it will use B samples to calculate the loss. Batch SGD uses the entire data set. Okay. And batch nag is again entire data set, but it will instead use a nag algorithm, entire data set. So which of these will have more oscillations? The question is which one of these will have more oscillations? So I hope you remember that uh, I mean, let me tell you the answer that SGD will have will have more oscillations. What is the reason for it? In SGD, I am considering only one sample at one time instant. Okay. What does that mean? So let's say I am at some point some point, let's say I'm denoting this my position by this red point. Okay. However, because of SGDIM, since I'm using only one sample, my that one sample will tell me, okay, I should go in this direction. Let's say I'm just constructing something. Okay, this is the point where my SGD will tell me to go. Now I say that okay, fine, this sample is done. Let me bring the second sample. Now the second sample will tell me, okay, go in this direction, something like this. I will come here. Now third sample will come. Third sample will tell me, okay, go in this direction. I will go here. I mean, similarly, I will continue. I hope my point is clear that if you are considering only a single sample, there will be a lot of oscillations. However, if you are using, let's say, more number of samples, let's say some B number of samples, so let's say B is 10. Okay. Now, if B is 10, then you have a better estimates of your gradient. That is the whole idea. So let's say if you are at this point, you move to this point. Okay. So you have 10 samples, you calculated the loss on this 10 samples and updated your took the gradient with respect to this loss. Now this 10 samples have, they told you, okay, go in this direction. Okay, you said fine. Now you said that okay, next batch of 10 samples should come in. That told you okay, go in this direction, something like this. You said that okay, fine. You now discarded this batch and said that okay, next batch. You took the next batch and then computed your loss. This it said go in this direction, and you kind of moved forward with like this. So I hope you can see that this will have a lot of oscillations. Okay, however, this doesn't. It's a relatively it is smooth. Okay, it has less number of oscillations. Uh, Another thing to note is that if you use a batch gradient descent, you won't have this many oscillations. In fact, you won't have any oscillations. You will, if you are at this point, it will directly say, okay, go to this point in just one step. Okay. However, the thing with it is that you will take a lot of time and it will be computationally inefficient. So this is the idea. Okay. I hope I was clear. If not, let me know. Okay. So if your batch size is small, you will take a more number of steps. In this case, you took a lot of steps. If your batch size is high, you will take lesser number of steps and you will directly go there. Okay. In that case, you will have lesser number of oscillations. So this will be the correct answer. And this option is, not important because NAG has an algorithm which is designed to reduce oscillation, so it doesn't really make sense. Okay. So if anything was not clear, you can ask me or we can move forward. Okay. So this was the sixth question. Now we have the seventh question. We are said that okay, we are training a neural network again at iteration t of weight updates with weights wt. Suppose using the momentum based algorithm, we cross the local minima and get to wmt plus 1. So if we use momentum, using momentum, we are at wt plus 1 m. Okay. And if you use nag, we will reach wt plus 1 n. Okay. This is a superscript that we are using. And we are asked which of the following statement is true. Okay. So let us do this. I think it is again a simple thing. I mean, by seeing the option, one might get, scared. Okay, what are these options? But let me assure you that it is not a big thing. It is an easy thing. Okay. Let me tell you how. Okay. So from momentum based update, we know that, wt plus 1 m will be equal to wt minus gamma times update at time step t. Okay. We know this. So if we substitute w update t here, what will it become? Minus gamma times update t minus 1 minus eta times gradient with respect to wt. Okay, this is what it is. Okay. Okay, all right. Now Wt plus 1n, which is with Nestor of acceleration. If you do similar thing, you will get Wt minus gamma times update t minus 1 minus eta times gradient of Wt plus plus eta times gamma gradient with respect to update t minus 1. This is what you need. So let us take this here and take the mod. Okay. So Wt plus 1, let us do this for nag first, n minus Wt. Okay. This will become what? Uh, Minus gamma times update t minus 1 minus eta times gradient is equal to Wt plus eta times gamma update gradient is equal to update t minus 1, and let me divide this by Wt plus 1 m minus Wt. So I am doing simple calculation, so this will come out of here. Okay, let me divide this also by what? Minus gamma times update t minus 1 minus eta times gradient with respect to Wt. Okay, so now I can in the options we have mod. We can take the mod here. Okay, fine. So mod, I can convert this plus to minus and minus to plus and my plus to minus. Okay, that won't harm me anymore. Now, okay, I hope you can see that, we have something which is plus here, gamma time update t minus 1, we have in denominator as well. So this is a constant. This is like a constant to me. I can ignore this term. Okay, so I can just write that this as eta times gradient. Sorry, my it is clear, right? Okay. No, I think it is. Oh, come on. So is my screen unshared? Okay, okay. Sorry, I was not seeing this. Let me reshare it. I'm really sorry. I didn't know why this is happening. So it is showing me that the screen is sharing. Is it actually sharing? I don't think so. Let me rejoin it from the tab. So is my screen visible now? Can you just confirm once? Or is it stuck? I think it is stuck. So can any one of you tell me if my screen is visible now? or is it stuck? Can you just confirm, any one of you? Yeah, Mudassir. So I don't know, your voice is not audible. Can you maybe write in chat? Are you trying to say something? Screen is still stuck. Oh my god. Okay, let me okay. Microsoft Teams with eta of sharing is visible. What is eta of sharing? I think there is some issue with my internet connection today. I think that is the only issue. I think. Oh, I see. There is some internet issue. Okay. Just give me a second. Okay. Okay. Now we start the broadcast. Well, now is it visible now? Uh, Thanks. Oh, I'm really sorry. I don't know. I will make sure from next time that these problems don't happen. Okay. So, what I was saying was, so we were asked that, we were given that at time instant t, we are using momentum and we reach, let's say, WMT plus 1, and using NAG, we reach WNT plus 1. Okay. We are given some option which has wt plus 1 minus wt mod as there is some we have to come up with some relation between wt plus 1 minus wt. So in some sense what we are asked is, okay, if it is this is wt, and if I reach, let's say, wt plus 1 m, and if I reach wt plus 1 n, what is the relation between this distance and this distance? Okay, this is what we have been asked. So if you think from, a logical point of view, common sense point of view, you would know that, this distance will be lesser. Why? Because nag is designed to, be near closer to minimum. Okay, so the whole motivation of NAG is that, you are close to minimum. However, for momentum, this is not the. I mean, you can go away from the minima as well. So there are a lot of observation oscillations that we observe in momentum. However, you can also see it from here. So what I did was I wrote the update equation for momentum, this thing, and for NAG, this thing, and I took this WT here, both the sides, and kind of divided them. Okay, and we observed that, you have something which is common here and here, so maybe you can just ignore those things. Okay, and then what you can do is take the remaining terms, gradient of wt minus eta times gamma times gradient update t minus 1 upon wt, which is again equal to, It is again equal to if I individually divide this, this will be gradient Wt upon eta times gradient with respect to Wt minus eta times gamma times gradient with respect to update T minus 1 upon eta times gradient with respect to Wt. This will cancel off. This will become 1. So this is 1 minus some quantity. Okay. So 1 minus some quantity. I hope you will agree that this will be this which will be less than or equal to 1. Okay. I hope if you are subtracting something from 1, it will be less than. Now, so what it means is that uh, mod of Wt plus 1 n minus Wt upon Wt plus 1 m minus Wt, this will be less than or equal to 1. What this means is that Wt plus 1 n minus Wt less than equal to current of Wt plus 1 m minus Wt. Okay, and this is the correct option that you will see in the options. Okay, so, let me just do something like this. So I mean, you didn't need to do all this mathematics. You could have just thought of it from a logical point of view. So this is Wt, this is Wt plus 1 m, and this is Wt plus 1 n. Since you know that Nesterov algorithm is designed to make sure that if you are closer to minima, you don't oscillate a lot. That means that this length L1, and if this length is L2, L1 will be less than L2, and you could have directly arrived at this option. Okay. So this was the seventh question. I am sorry for the hiccups that are happening today. Okay, I really don't know why it is happening, but really sorry. So there is a eighth question which says that we are using line search with the following eta. So the eta range that is for given for uh, line search is as follows: 0.1, 1, 0.5, 0.01, 0.01, and 10. Okay. At the nth iteration, eta was selected to be 10. Eta was selected to be 10. What can we infer about gradient of W? This thing. And we are given that this is positive. Okay. So okay. So what it is saying is that Wt plus 1 is equal to Wt minus eta times gradient with respect to Wt. So or Wn maybe. So T is equal to n here. What it is saying is that if we choose the value of eta, this eta to be equal to 10, we get the best update. Okay, this is what it is saying. So what does that mean? So eta is equal to 10 is like a large step. We are taking a very long step, and that is when we are getting the best result. If we are taking small steps like 0.11, 0.5, or this thing, we are not able to get the best option. This is what best so this is what line search means. Okay, you try different eta and you choose the eta which gives you the best update. It is saying that the best update is given by eta equal to 10. So how should the curvature look like? How should the loss function look like? Whenever you are given these things now, what step size? Try to imagine the curve that it is, descending upon or updating upon. So for this, the curve that comes to my mind is the following. Okay, so something like this comes to my mind. Why? Because you can see here the gradient is very small. Okay, however, it is saying that even if you are here in this, if and you have to move in this direction, take a big step, eta equal to 10, and come directly to here. This is what it is saying. So, so instead of going from here to here, you will go from here to simply here. This is what it is saying. Okay. So, what is the so when this type of thing will make sense? When your this thing gradient of Wn, this is small. Okay, I hope you can see that. What kind? So you can just argue with me. Okay, that okay, why should I trust you? So I will say that okay, let us consider something like this. So in this case, let's say you are at this point and your gradient is here, and now you are saying that okay, instead of going from here to here, take a huge step size, okay, and go from here to here. I mean, if you take in this, if you go in this direction, you are saying me, okay, don't take a small step, which is this thing, take a big step, and you will take me from here to where? Some point here, right? Which is not good because you have missed your minima, which was this point. So I hope that I'm able to articulate myself. Okay, if your eta, the best eta is, a large number, then that means your gradient must be very small and you are in some sort of flat regime, something like this. Okay, so this will be the correct option. If I mean, this is just a simple, common sense question. If you have any questions, maybe I can ask me and I will clear that question. Okay, clear your doubt. So you have a ninth question. Which of the following are among the disadvantages of ADA-grad? So, okay, what are the options? Doesn't work on sparse metrics. So we know that, ADA-grad is designed to work well on sparse metrics. So that is not the correct option. So this is not the correct option. We have B option. It usually gets past minima. So this is also not correct because AdaGrad, updates your learning rate to be smaller and smaller as the time progresses. So it cannot, pass go beyond the minima. Even if it goes, I mean, this is not a disadvantage of it. It will come back. It won't happen that if it misses the minima, it won't come back to minima. It will come back to minima, but it is not a disadvantage of it. So this is also not a correct option. So there is a C option. It says that it gets stuck before reaching minimum. Before reaching minimum. So this is a reasonably correct answer. Why? Because if you remember the ADA grad update that we discussed, yeah. So this was the ADA grad update. You can see that So what we are doing is that we are adding something to your VT. Okay, so as time progresses, something will get some positive quantity will get added to your VT always. Okay, so at time t plus one you will have gradient of WT plus one square that will get added and so on. So as time progresses, you are increasing your denominator that is here. Okay, and if you are increasing your denominator, you are making your learning rate small and smaller and smaller and smaller. Okay, I hope that part is clear. So if your denominator increases, this entire term decreases. Okay, that is like basic maths. Okay, and if you decrease your learning rate a lot, at some point, let's say it becomes, let's say 0.000001, something like this, which is almost zero. Okay, it is not exactly zero, but it is very close to zero. And in that case, what is happening is that this term is becoming zero, and hence there is no update at all, and you are stuck at WT. I hope that I am clear. And in that case, what will happen is that before reaching the minima itself, you will get stuck, and hence this is a correct option. Okay, C is the correct option. And there is a D option which says that weight updates are very small at initial stages. Are small at initial. So again, this is not correct. There is no reason to believe this, okay? Because we know that there is no such things. If anything, initially the weight updates are more high because your learning rate are high initially, okay? So this is also wrong option. So this was the ninth question. Again, if you have any questions, you can ask it right away, okay? And then there is a 10th question which says that what are the advantages of using STD instead of vanilla gradient descent? So advantages of STD over normal gradient descent. Okay. So whenever this thing comes up, there are only two advantages of using it. Okay. First is faster convergence. Since faster convergence, and second is computational efficiency. So why faster convergence? Because so think of the vanilla gradient descent. Okay, if when it takes one pass over the data, it takes only one step. Okay, whereas if you use SGD in one pass over the data, it will take, let's say if there are n data points, it will take n steps. So so here it will take n steps in one epoch. So epoch refers to one pass over the data. Okay, whereas SGD will take one step. Okay, one step. This is for a normal gradient descent. So obviously if I am taking more number of steps at each uh, in one pass over the data, I will converge more fastly than the normal gradient descent. Similarly, computational efficiency is there. Why computational efficiency? Because I have to process only a single data, process single data instead of whole data set which contains, let's say, n data point. So if you have to process a single data point, it is much efficient as compared to processing the all the data points in your data sets. So that is why it is also computationally efficient. Okay, so these are the two options. I think there are two options that are there in the options which are correct. Okay, so by this I think we have solved all the 10 questions. If you have any questions, please ask. Or there were a lot of hiccups today. I'm really sorry for that. I don't know why there is some internet issue. I suppose with the ISCW land today. I'm not sure why it is happening. But nonetheless, if you have any question, go ahead and ask. Or if you have any suggestions that okay, uh, I can improve these lectures in any way, or maybe if you thought that this was good or bad, your feedbacks are welcome. Okay. So if there are any questions, you can just unmute yourself and ask. Okay, no questions. Okay. So I know there were a lot of hiccups today. Some part you were not able to see. So I will make sure that from next time onwards this won't happen. Okay. Uh, if there is anything else, let me know. Uh, so can you unmute yourself and maybe speak because this has been a bit monotonous thing today. Yeah. So I don't know. Maybe you can see that you are unmute, but yeah, yeah.
But
Now your voice is audible.
okay, so I don't have any questions. I got understood.
Okay. So you were not clear. You said that you understood. What is
Yes.
there anything else?
No, that's just the resharing of screen. Whenever anyone comes late, you have to reshare the screen in Teams, I think.
Yeah,
Even though
I
you
don't know why it is happening. Yeah, 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 right. Yeah, you're right. I don't know why it is happening, but from next time
it's
maybe I will make
only
sure that
their
it doesn't
side
happen.
only, software side only. That is,
Oh, I see. Oh, is it?
I
Oh,
searched
I
on
didn't
internet.
know.
Many people had that problem. They haven't resolved that.
Okay.
Yes.
Okay, I see,
Thank
I
you.
see, I see. Okay, thanks. Okay, so was the lecture okay or was it like bad or any feedback from
Yes,
your
sir.
side?
No,
Excuse me, sir. It's a very good lecture, sir. We understand your problems. Thank you very much, sir.
Okay, okay. Thanks a lot. Okay, thanks a lot. Okay, so if there are no questions, then maybe we will end the meeting. Okay, thanks a lot. Thank you for joining.
yes.